Welcome everybody to our Science Thursday with Brookhaven Lab. The goal of Science Thursdays is to engage our student and education community in STEM topics by meeting Brookhaven Lab STEM professionals and learn more about their work and their career path that got them to where they are today. We hope that at the end of this 45 minutes or so, you have heard something that will spark your interest in a STEM career and perhaps even consider being part of the Brookhaven Lab community. So my name is Aleida Perez, and I am from the Office of Educational Programs, and I am joined today by Salvador Gonzalez, who is behind the camera, sharing and leading, taking care of the recording for today. So before I introduce our today's guest, a few reminders. Submit your Q&A questions on the chat, on the Q&A chat section, which is at the bottom of your Zoom app. And we will try to get as many questions as we can. And if you have any issues or concern, just let us know by sending us a note through the Q&A chat section. So today I am joined by Simerjeet Gill. She's a materials scientist, deputy chair and group leader at the Nuclear Science and Technology Department here at Brookhaven Lab. Simerjeet will share with us her work and her career path with us today. So you're welcome to put any questions you want on the chat and we will try to get as many as we can. Simerjeet, welcome. It's a true pleasure to have you here today. I know we're trying to find a date, because our busy schedule. So it's truly a pleasure that we can do this today and looking forward to today's conversation. So before we get things started, how long have you been at BNL?
I've been here 12 years.
Well, wow. Where were you before?
I did my graduate studies in porous materials at Texas Tech University. And after that, I joined as a postdoc at Brookhaven Lab. And then, I was assistant scientist, associate scientist, and now I'm deputy chair of Nuclear Science and Technology Department. And I can tell you it's been an incredible journey so far.
Awesome. So you came and you liked it so much that you just could not leave us. Basically.
Yes.
That's why we're saying yes. I'm glad that we're here today because I don't think people know that that your group exists at BNL and we have been here for a very long time. So can you tell us a bit about what is it that what is the research that goes on at the Nuclear Science and Technology Department, and what is the mission? What is it, the research that goes on in your department?
So our department conducts research and development to support various nuclear technologies. We do R&D for nuclear reactors, accelerated different systems. We work in various areas of these nuclear technologies, which includes studying the performance of materials in extreme environments, which is the focus of my group. But in the department, we have great scientists that work on many other aspects of nuclear technologies, which include reactor physics, thermal hydraulics, structural mechanics, human factors, mechanical engineering, risk analysis, and nuclear physics.
So it looks like a very broad range of skills and topics that are covering your department. So for the folks out there, think about, where, you can apply your different skills at some point in your life. So this is awesome. So you mentioned that you are a material scientist, and I think this is our first material scientist that we have on Science Thursdays. So for our guests, what is a material scientist? What is it? What do you do? What is a material scientist?
So in my opinion, material scientist is a person who synthesizes and studies the structure, physical and chemical properties of the materials. So we study as-made materials. That is, when I say as-made, it's like when we synthesize them. And then we also study the performance of materials in various environments, such as high temperature, under mechanical stress, when they're exposed to corrosive fluids, when they're exposed to radiation. Of course, these are the environments that exist in nuclear reactors, but there are also environments that exist in many other applications. For example, batteries have corrosive fluids. There are other high temperature environments. There is stress in many other real life environments. And then we use this knowledge of properties to optimize and improve the performance of the material so that we can make more efficient materials. We also engineer materials, or say design materials that are corrosion and radiation resistant. They can survive in these environments much better.
Very cool, very cool. So material scientists, so you're looking at not just looking at the various properties of materials, various environments, and how these environments impact the functionality of those materials in whatever setup they are being used at, whether it's a reactor or a battery and such. Very, very cool. You mentioned that, now that you mentioned, when you and I were talking a little about, and you just mentioned there, your group specifically focuses on those materials in those very extreme environments. So when you think about it, when two things are coming to my mind. What are those materials that you look at? And when you talk about extreme environments, what do you mean by extreme environments? They are very, I always think about temperature and so forth, but there's more than that.
Yeah, so I believe your question is, what are the materials, right?
Yeah.
So the materials are since we are focused on nuclear applications, we study nuclear structural materials. For example, stainless steel, nickel alloys that are used in structure of a reactor, in piping and various parts of the reactor. We also study fuels, which are uranium-containing nuclear fuels. So those are the kind of materials. We call them high Z materials because they are made from heavier elements as opposed to carbon, silicon, which are low Z materials. So those are the materials we study. But we've also studied some other construction materials like cements, like, how cement survive these extreme environments. And for extreme environments, we study high temperature. Of course, that is part of our current reactors, like pressurized water reactors, boiling water reactors. So we study high temperature. We study corrosion, where we study materials in corrosive environments. For example, high temperature steam, molten salts, and acids. There are basic environments, brines are present in geothermal wells. So we study those corrosive fluids. And the third kind of extreme environment that we often encounter is the radiation. Of course, there are neutrons present in nuclear reactors, but neutrons make the materials activated. They become radioactive. So we do study some activated materials in our group, but we also, to understand what radiation does to these materials, we also do fundamental studies where we ion irradiate these materials. We shoot ion beams such as helium, iron on these materials, and then we study what these beams do, how they knock off various atoms from these from the structure, from the lattice. When the atom goes out, we called it as an interstitial, and it creates this empty hole, which is called vacancy. So these are called radiation-induced defects. So we study what kind of defects are produced, how do they come together, like vacancies come together to make a void, and so we study radiation effects in the materials.
So by having how the effects of these very extreme environments, you learn to the behavior of that material over this behavior of the material over time, and how that may impact the structure, the functional structure, let's say, of the nuclear reactor in this example. Would you say that's one of the goals of doing this kind of studies?
Yeah, so goals wise, we do both fundamental science. In fundamental science, as I said, we study the mechanisms, like what is happening at atomic or molecular level in the material structure. And then we want to study how, the material is changing. But then we are also concerned with the performance of the material. We actually see what kind of defects actually are produced in the material. For example, we see cracking, we see if in radiation, we see swelling of the materials. I'll quickly share an example where we were imaging the crack in one of the materials. Let me see if I can share my screen here.
Yeah, we see
Do
it.
you see my screen?
Yes.
So in our group, we use synchrotron techniques, which are, as you know, at lab, we have National Synchrotron Light Source 2.
Mhm.
And here is an example where we studied the corrosion in a stainless steel. So this region right here is the grain boundary where various grains meet. And this was subjected to acidic sulfuric acid environment. And we were able to do the 3D imaging of the material and study this crack. So this is the actual performance of the material, where material cracks. And then mechanistically, we were able to see this is the elemental mapping, where we can map out all the elements. So this is a iron-based material. Of course, it's a stainless steel. And in green, we see this chromium segregating at this grain boundaries. We see all these chromium carbide precipitates, and these are the precipitates that weaken the material, making the site of attack and making it corrosion susceptible. So by doing this, we were able to see that how the material cracks, when it cracks, and why it cracks, what happened to the composition of the material that led to the cracking. And we were able to correlate this and see this intergranular cracking, and what we call is the selective dissolution of chromium in this case, but in general, we call it selective dissolution of elements, and related to the corrosion performance of the material.
That's actually very, very cool. So actually, I found it fascinating that you can actually, these tools are very, the light source and that we have had at the NSLS too, very sophisticated, that you can pinpoint out what is the source, what is causing the elemental cause of this corrosion that lead to the fault, the damage of that particular piece of material.
Right.
Is your group, some of the research that you do you collaborate with international groups in terms of reactors and reactor safety in the United States and other parts of the world?
Yes, we do work with IAEA. My group doesn't directly work with that, but we have international collaborations. In the past, we have worked with CEA Macoul, which is another nuclear lab in France, where we studied the corrosion, and we studied the absorption of fission gases by Prussian blue analogs. We have had international collaborations in our group, but we routinely collaborate with international groups in our department.
And so is the end goal, by understanding this material behaviors, is at some point that we are able to build perhaps some more I don't want to do a sophisticated, but more secure, more stronger lasting reactors that that can withstand, let's say, earthquakes or any kind of extreme environmental setup that may happen during time.
Yes, so we do all the 3 steps. They're called inform, predict, and design. So by doing our experiments, we gain the knowledge how the material behaves, right? We produce the fundamental knowledge of material performance. And then our data can be fed into the predictive models that predict the long-time behavior of the material. And then design is where we come up with these strategies that, okay, like for example, I showed you an example where the grain boundaries were the site of attack, right? How can we engineer these grain boundaries? It's called grain boundary engineering, to make the material more corrosion resistant and more radiation resistant. So we do all the 3 steps. We inform all the 3 steps too.
To our audience, you can put your questions in the chat in the Q&A section, and we'll take them as they come in. I know you talk about nuclear reactors as perhaps the one that your main focus, but are there any other applications in the time of research that you do? You mentioned cement, but are there, besides those, are there any other applications on your research that you do besides nuclear reactor?
Currently, the projects that we have currently are mostly focused on nuclear. But as I said, we've had some portfolio in geothermal energy where we studied the cements which are used in the geothermal wells. We studied the interaction of cements with the steels, which are used at casings in these wells. So we've studied materials for geothermal applications, and those are the two main areas that we focus in our.
Very, very nice. And so when, so I guess we answered this already, but I will ask it again. So where do you think your field is heading in the future?
I think there is a lot of progress made in material. So I'll answer this as a two-part question. First is the materials. I think we are in the era where we are making really functional materials. We have advanced manufacturing techniques such as additive manufacturing. We have a lot of new functional materials. We are in an era where we can do bottoms up design. We can really engineer really functional materials. And for nuclear, I think nuclear is a very efficient source of clean energy. So I think we are in a position to really contribute towards our decarbonization goals and clean energy goals, which we as a nation in US are set to achieve. And of course, there's a global emphasis on decarbonization and clean energy. So I think this is a very happening era for nuclear, where we have these advanced designs such as small modular reactors, which can be run safely and much more conveniently, making nuclear more accessible, not just as a pure nuclear, but also as a support source of energy to other energy options.
Yeah, that's actually good. I know that I've been, in reading in literature, one of the goals is really to get those reactors smaller and more efficient, right? So the material piece is part of that. And so that is something that is cool. Before we kind of shift to your career path, you are a user of the light source. And is that the main tool that you use to do your, to understand better what happened, the impact of this environment to your materials, or do you use other tools as well?
We do use other tools as complementary techniques. For example, we use microscopy to gauge that level resolution. We also do some DFT-based modeling to support our experimental results and sometimes even fit our data. So definitely synchrotron is our main technique, but we use supporting microscopy and DFT models. Was the connection a little shaky? I got something on my screen.
It's a little shaky. It's part of the internet world these days. But we got you, Simmer.
Okay, yes. So in short, I was trying to say, yes, we do synchrotron-based methods, but we do complement them with electron microscopy at CFN, and we do our DFT-based modeling also.
And I find that stuff that you work is very interesting because, knowing what makes them, what the materials behave, you don't want a reactor to go, crazy because you don't know what those, the surrounding material that makes up that structure behave. So I look at it as a good way to prevent, right? The more you understand, the better you build, the better you prevent malfunctions or catastrophic events in the future, so that it leads to a better function of the tool. And so I think it's actually very cool, the work that you do. I learned something today. I'll be very frank with you. I learned something today. So let's do a quick shift to your career path. You mentioned you've been in BNL for some time. Did you just wake up one morning and say, I am going to be a scientist? That may have happened, but what is it that, how did you know? Do you always know that you wanted to be a scientist?
I don't think so. I think I was genuinely curious. I used to like think about simple stuff like, when we bake our bread or make our cakes, why does the dough rise, right?
Mhm.
Or, simple stuff. So I had genuine curiosity of everyday science, but
Mhm.
I think the two things that had contributed a lot for me ending up as a scientist were that I had a great science teachers that really helped me to, that cultivated my interest, gave me the right experiences. And
Mhm.
second was exposure. I think I did participate a lot in science competitions. I was on the teams, and that helped me to become better. And that being better again reinforced my. So it was like an ongoing symbiotic relationship. So I think both, like getting exposure to the science facilities and science workshops, having great teachers,
Mhm.
both helped me to really decide to pursue a career in STEM.
So that was a question that came on the chat about your role model. So you mentioned your teachers being a role model
Mhm.
as a young student. Anybody else besides a teacher, any other role models that you had growing up that may have influenced or at least nurture that interest in STEM?
Well, he was not really a role model, but I think my father had a lot of influence on me. He was a deputy director in a fisheries department, which
Mhm.
is like a department that is responsible for natural water reservoir, and they are responsible for the health of fishes in these reservoirs.
Mhm.
So to make sure that they have healthy fishes, they had to do lot of these measurements.
Mhm.
And my mom had a very remote job. So usually my father would pick us from the school and we would be at these fish farms that, he would oversee. And they are supposed to take like periodic readings of how the water quality is. And, they had like little tadpoles around to see how the health of the fishes are. And I would see them in the microscope. So I think early on that kind of exposure and okay, okay, we need all this data to really understand how the fishes are doing. I think that in the background did train me that how we take observations, how we collect periodic data, and how we compile trends to really understand and convince ourselves that this is I mean, in that case, it was like that the fishes are healthy, but to really come to a conclusion on what we are observing.
Yeah, that's a great story, Simmer. Yes, that's a great story. I can just picture, helping the family, your dad collecting like a little lab assistant, right?
Yes, yes. And
I
we
love-
were like, he was stuck with us because my school will get over till 3 and he had to work till 5. And we would just like, roam. We were like, yes, as you said, little unofficial workers of their department who would like go collect samples and look at of course, they didn't take our observations seriously, but at least I learned how to use a microscope.
That's a great story. That's a great story. So did you follow a linear path in your career, meaning that you went from undergraduate to graduate school and then postdoc, or did you take some detours along the way?
I did take one detour. I believe it or not, I was a high school teacher at one point.
You
So,
did.
yes, yes.
Oh,
I along with my bachelor's and master's in science, I do have a bachelor's and master's in education. So I taught high school students for 3 years. And it was a fun experience. And in India, where I was a teacher, you are used to you are say posted in rural area for
mm-hmm.
your initial years of service, and that gave me exposure to how the schools were there, because I was always a city kid, and it was a lot of fun explaining students about the various concepts
Mhm.
And so that was a little detour that I did take, but then I did miss being in the lab quite a
Yes.
bit. So I decided to, go and pursue my doctorate in US.
That's a great. When you and I spoke, that was a nice surprise in this conversation. I'm assuming that you, what grade level did you teach? High school, you mentioned?
So I was officially responsible for 8th to 10th, but then we had this primary school, and it was really like a good experience. So they became our legacy because their school closed for some financial reasons. So believe it or not, I did teach kindergartners and high schools students together, which gave me like experience of both sides of spectrum.
Yes,
And
that's
I
awesome.
think like explaining, you would think that just like explaining or making kindergartners learn science and math is easy, but I found it even more tough to make them grasp the concepts
Yeah,
than the older students.
I think it gives that perspective of scientists and how we communicate how we communicate our job, our work, and how others, so this in a way that is understood, right? Not just by our peers, but by everybody else that surrounds us. This is a great story. If we ever need a sub, I will call you, Simmer.
Sure, I'll be happy.
So, and then you came here being as a postdoc and you stayed. So, and now you are a deputy chair of your department, which is a great story. Not a lot of women in that position at the laboratory. So this is great to have a role model in that as well. So if we have students who want to kind of follow your line of science, what would you recommend in terms of, you want to be a studying material science, and what kind of courses or kind of preparation, not just at the high school level, but perhaps also at the college level, a student should think about, in order to get them ready for this type of career, of this type of science that you do?
Again, I think like genuine curiosity is very important. Like,
Mhm.
genuine curiosity and passion for the field. Of course, science is a diverse field, and of course, you need official courses for, being trained so that you have the basic fundamental knowledge of, say, material science, or if you want to be a physicist, you need to know your basics, fundamental physics.
Mhm.
But other than that, I think being hands-on, I was always a hands-on person, so abstract courses, I just like sort of passed along because they were needed for the degree. But I much more enjoyed the experimental aspect. And maybe that's why I became an experimentalist.
Mhm.
And I think like having genuine curiosity and passion for what to do takes you a long way. It becomes much more enjoyable to learn concepts when you have an actual real experiment to apply it to. It becomes easier, it is much more enjoyable. It also is your self test to see if you really would want to do that.
Yeah, and I think that's the value of the internships, right? We talk about, the Department of Energy has a series of internships to college students through the science undergraduate laboratory internship. Even high school students can participate in high school research program and other opportunities, because the internships give you that exposure that you just mentioned, and then you can
Mhm.
start to see, hey, this is something that I can see myself be part of in the future. Did you do any internships when you were an undergraduate, that you had that opportunity to do?
I worked across the labs, in the sense, not like within the department, we had different faculties. My focus was on nanomaterials, but I did work in another faculty's lab, which was work. That was a very interesting project, and that's why I ended up working. So they were doing this project for forensics. I actually have a publication out of that project. So their job was to elucidate the fingerprints And my job was to make these nanoparticles. So we took like fingerprints on the slides, and it was my nanoparticles that illuminated that fingerprint so that we could learn, whose prints they were, and we could learn all the details of fingerprints. And believe it or not, that was a very small summer project that I had done. But whenever I presented in my whole research, I would get most questions on those two slides rather than what my major thesis was, which was aerogels and xerogels for catalysis and sensing applications. So you mentioned internships. I think internships is a great way. It does three things for you, right? A, you see all the scientific infrastructure, like we have National Synchrotron Light Source 2, which is like an X-ray source to study materials. We have CFN, where we have all these advanced electron microscopes to image the materials. So you get exposed to all these scientific facilities that exist. You see your day-to-day life. So you see what a scientist does in everyday life. I think that's very important, rather than just thinking what scientist does. Being in that real environment is something that is very valuable, that comes out of internships. And third, which is very important in today's day and age, you become a member of the team.
Yes.
Like in national labs, we have world-class scientists. You work in that team and you see the entire process. Like in our field, we start with experimental design. You have to have a good hypothesis that, okay, I'm going to do this study. This is what I'm going to learn, to which I can say yes or no to after this study. What do I need to do systematically to really get to this goal? And then you perform the actual study, you collect the data and you analyze the data. And then once you cannot make sense of the data, or if some aspects of data is challenging, we sit and brainstorm as a team, and you learn and see that everyday science process happening, and also how, you also learn all these other soft skills, working on a team, discussing with people, seeing the value of various ideas that come to the table. And sometimes out of discussions, another colleague may come up with a point that you have never thought about, which may be very valuable to make sense out of your data. So I think internships are valuable in all those three things. You see with your eyes, you live the life of a scientist for some time to some extent, and then you get the exposure to the infrastructure, scientific infrastructure, and then you work with this world-class scientists where they can really inspire you to think about the data in certain aspects.
I think you said it very well, and it brings all. It said it very well. And what I like the most that you mentioned too is that the understanding that science is collaborative. It's not, it's not like it's just one person coming up with these ideas. We all come with this. Everybody come with a different perspective. At the end, we put them all together just to answer or solve a problem. And so that's something that is, that students sometimes, when you're young in your career, you tend to miss those points. And so it's getting those ideas early as you plan your journey is very important. So internships when you can, and when available and possible, it's an opportunity that is, if presented, students should take in. You have been a mentor for us, right, Simer, on our programs, into our college students here. So what have you learned from this interns that you have mentored over your time, and how has that impacted you in terms of your career in the science that you do?
Oh, I have learned from them immensely. We have students that come from various cultures. We collaborate with University of Puerto Rico, So definitely, we've learned. I learned about different cultures, and with students, we've learned how different kind of students think differently, right? And the value that they bring to the table. So I think sitting with students and making them learn science. And sometimes, they may ask me a question that needs to be where I need to break down this really complex idea into very simple words.
Mhm.
And I am told that that is a skill that goes long way, because think of it at a higher level, right? You are facing a program manager who may have a very limited training in science, but you are sort of trying to get funding and selling your idea. So
Mhm.
I think it's all about knowing your audience to whom you are talking, and also dealing with all these different students. I think it is a reverse training as a manager too. Like, you do get flavors of different personalities, so definitely it enriches us.
Mhm.
uh, no question about it.
Yeah, and that was gonna at least leads me a little bit to ask you the kind of talk about a little bit about the importance of inclusion and diversity, which is one of BNL's core missions and values that we have here at Brookhaven Lab. And you just talked about how important it is to having a diverse and inclusive STEM community. What do you suggest that we do? What do you suggest that we can do to encourage those underrepresented group, women, people of color, people in underserved areas, to be part of our community? What can we do to increase that diversity?
Yes, I think diversity is very important. And it's a proven fact. Like, there are reports on it that when we have diverse teams, right, we have a more comprehensive view rather than just one set of individuals
Mhm.
thinking in a one specific way. When we have team with diverse ethnicity, diversity in many different directions, right?
Mhm.
Diversity of thought, diversity of point of view, definitely you travel in a wider space, and definitely your solution set becomes bigger. So the chances are you are going to come up with a more effective solution if you have a diverse team. Now, coming to your point of how can we increase diversity, I think better outreach. We must reach out and present our capabilities and sort of educate people in minority institutions about what we offer as a national lab complex, right? And second is having role models. I think that is very important, because when you see represent, we also call it representation, right? If you see a person who you can relate to, definitely you are like, young students are wired to think like, okay, if he or she can make it, I
I
can make it too, right? And then also there is a real life story, right? Like, today we are talking about the stories, you know what worked for you, what didn't work for you. Having those role models, that representation, and those mentors is very, very important. And I think by working on all that, we can really increase diversity, and it needs to be increased at every level. Like, we need to go from at diversity is important, not just at the early career stage, not just hiring diverse candidates, but retaining them. Like,
Mhm.
what, I don't think it's so beneficial if you hire a diverse candidate, but that candidate doesn't have a conducive environment or a prosperous environment. Retention is equally important. And then, that making sure that that person grows and we have representation at higher levels, that is equally important. That's when we will achieve like a diversity in its entirety, I believe.
I think it was well said. I agree with you. I have nothing more to add. I think it's well said, and that we all should take. It's a topic to take from the top down and the top bottom, from the bottom to the top, and the top to the bottom. Everybody should focus on. There's a question on the chat before we go that I want to ask. It's asking about what kind of and how accessible are internships for pre-college students. I can know this, from Vienna, we had the high school research program, which is something that we do for 11th and 12th graders. But there are other institutions around Long Island that do offer internships programs for pre-college students. The Stony Brook University, It's one of them. They can check also into Hofstra and other local universities as well. But at BNL, we have the high school research program, which is our program for high school students and providing my authentic research experience. If there are any questions on the chat, before we depart, this has been a very joyful conversation. I learned about not just about your research, Simmer, but I also learned a little bit about you as well. If our audience just didn't pay attention because the sun flares were conflicting with Zoom or all these pieces there, what kind of 2 or 3 final advice you will want them to take home message you want them to take with for today? 3 pieces of some final advice for the audience.
I would say try a lot of things. Try, as much as you can would be my advice. Fail often. I always say I learned much more from my failures than my successes. Like, that thing when you really get hurt and you're like, okay, and you make a mental note, this is what should not be done. It is important to know what to do, but it is equally important to know what not to do. So do a lot, try different things. Second would be talk to a lot of people, reach out, when you have don't think think profession as your life. Reach out to people on LinkedIn. You can make like great relationships in a professional life too. So talk to lot of people. If you're curious about any area, and you may be curious about 4 areas and they may not be related at all, I would reach out to people in your community, reach out to people through professionals websites like LinkedIn, and you will be surprised how generous people are with their time. And you could schedule short chats, and you can ask them, what does your everyday work day look like? Gaining that first-hand knowledge is really important. And last but not the least, be optimistic. There will be days where you'll be like, oh my God, what's going on? But I think to be optimistic, just to take a pause and be optimistic and just keep working. I always say hard work always pays. You may have little moments of pause in your journey, but in the end, if you are motivated and you work hard, you will reach there. And you can take my word for that. And you can, sort of ping me. You said that if I work hard, I'll achieve it. I'll put my money on that, I would say.
Thank you, Simmer. Thank you so very much for that. I think it was one of my most enjoyable summer Science Thursday we had in a while. So thank you so much for today, and thank you for your time. And I really appreciate sharing the work that you do and having to tell us why we should care about understanding the kind of the work that you do, and the importance of understanding material science. It matters, and it's a reason why we have to understand how these materials behave if we want to, in this case, understand a better design what these nuclear reactors will be for the future. And thank you for sharing your life experience and your career path. It was truly wonderful, truly wonderful. Please always tune in for our next Science Thursdays, and we would like to thank Brookhaven National Laboratory for hosting Science Thursdays, and we encourage you to check out our programs. You can go to, and I probably will ask Sal to put it on the chat, www.bnl.gov/education. We are offering a summer science exploration programs, week-long workshop for elementary and middle school and high school students. Please check that out. And follow us on social media. Thank you, Simmer. Thank you, everybody. Everybody have a wonderful, wonderful day, and see you next time.
Thank you for having me. It was a real pleasure and honor to be here. And I've put my email in the chat, which is gills@bnl.gov. So feel free to reach out to me directly if you have any questions. Thanks, Aleda.
Thank you, Simmer. Thank you. Have a good night, everybody.